Okay, so this is our finale. We are final exam review 4. So we've done a lot of different things, talked about a lot of different things. Hopefully I won't miss anything, but what we haven't talked about yet is momentum. And momentum is really inertia in motion. And the two things that momentum depend on are mass and velocity. So if you increase mass, you're going to increase momentum. If you increase velocity, you're going to increase momentum. So when we look at it algebraically, right, it's going to be P for momentum is equal to mass times velocity. And these are inverse, and these are direct. So if we're trying to keep our momentum the same, so if momentum is the same, and we increase or we double our mass, we're going to have to decrease our velocity by 2, by a factor of 2, in order to keep that value the same. So that is momentum. You can come in, Dodgers. It's okay. Let's see. We also have momentum equaling a change in velocity, or a change in, or impulse equal a change in momentum. Okay, so remember that impulse is force times time, right? It figures in how long you apply the force for, and that's equal to change delta. Momentum is mv. We already set it up here. Remember, too, that F and T are inversely related. So if I just take impulse out for just a second, okay, and let's talk about that for just a second. I can have the same impulse 2 different ways, or lots of different ways, but I can have a very tiny force and a really large time. But I could also have the same identical impulse if I have a very large force and a very little time. So let's say that this value is 5 and this value is 1. But it could also be 5 times 1 over here. So it's going to multiply basically to give you that impulse. So impulse isn't the bad guy when we're talking about car crashes or keeping you safe as a driver. Really what we're talking about is how impulse breaks down into the force time component. So the longer you give yourself to stop, so that's why you want to keep 3 car lengths between you and the next car, which rarely happens in LA. But you have airbags, you have seat belts, you have padded dashboards, you have all these crumple zones, you have all these things that are trying to basically do this for you to lower the force of impact on you. So impulse is not the culprit, it's really how that impulse breaks down, right? So force and time are inversely related. If you have more time to slow down and stop, you're going to have a smaller force. If you have very little time, you're going to have a really big force. But this impulse creates the change. So this is kind of like cause, and this is the effect, right? When you apply a force to something for a certain amount of time, what you're trying to do is to change the position of something. And when you're changing the position of something, you're changing how fast it's going or what direction it's going in or something like that. Remember, too, that this equation, Ft equals change in mv, is really Newton's second law. There's lots of flexibility in problem solving this. So this is the same as saying I equals change in p, right? Or I equals m delta v, or Ft equals delta p. All these things are basically the same. Okay? When I'm looking at making this Newton's second law, most of the time we're changing the velocity, so I'm just going to move this delta next to the v. So I have ft equals m delta v. I'm solving for f, so if I divide out t on both sides, I'm going to have f equals m delta v over t. And probably remember that delta v, the rate of change in velocity, is called acceleration. So really I get f equals ma from all of this. And I'm just doing a video. You can come on in. I'm just doing a video. It's okay. Yeah. So that's f equals ma from basically the impulse change of momentum equation. But there's a lot of flexibility built in. You know, I could ask you for the impulse, but not give you ft and give you how the momentum changed. So initial momentum and final momentum. I could give you the mass and the change in velocity and find impulse. So, you know, I may deliberately not give you ft, but you could solve it using other things. So there's a lot of flexibility there. Maybe the last thing to really talk about is work. So the concept of work. So the concept of work is really about, remember that definition of energy. Energy is the ability to do work, and work can be positive, and work can be negative, but it is not a vector quantity. So the positive and negative don't actually have to do with the directionality of the work, but it has to do with the cosine theta between the force vector and the displacement vector. So when we look at the equation for work, we say work equals FD cosine theta. And anytime it's cosine 180, it's negative work. And anytime it is cosine 0, it's positive work. Anytime it is cosine 90 degrees, it is no work.
Isaac Wolf, please come to the office. Isaac Wolf, please come to the main office.
All right, Isaac, get to the office. Okay, so a particular example would be, so if I have this box and the net force, right, is this direction. We'll say this is the applied force. Say that friction is this way, and the displacement is also this way. Your change in x. Must be another problem proposal outside. So if we look at our net force, it's going to be in this direction, and our displacement vector is going to be in this same direction. So there's actually no degree difference between those angles. And in that case, cosine of 0 is basically a positive 1. When we do it the other direction, okay, notice I'm going to now have my applied force this direction. My displacement is still in that same direction. My friction is opposite that. Again, my net force is this direction. Change in x is this direction. This is a negative. These are negative directions, right? But really what I'm looking for is the difference. The angle difference here is 0 between this head and this head is the same direction. So again, cosine of 0 is still that 1 value. So I could have both of my forces and my displacement going. What's up?
Oh yeah, it's just.
Okay, so we can see that it doesn't matter whether I'm going to the right and both are going to the right or both are going to the left. That has nothing to do with the directionality. It's really about the difference in the angles of that force and that displacement, right? So positive does not indicate direction. It actually just indicates the angle difference between the force and displacement vectors. In the case of cosine of 180, so if I have for example, I've started this object into motion, but now the only thing acting on it in the horizontal direction is friction, but it's still moving forward. So my force vector is this direction, right? My displacement vector is the opposite direction. So to go from this direction to this direction is 180 degrees, and cosine of 180 is a -1, right? Remember that friction can only do negative work on something, but interestingly enough, gravity can do positive or negative work. So if I toss an object up into the air, right, the displacement of the object is up, but gravity still is trying to pull the object down. And in this case, Fg does negative work on the baseball. But when the baseball is at its highest point, right, its velocity is 0, its acceleration is still 9.81 meters per second squared. As it begins to fall back down, its displacement is down, and so is Fg. Fg doesn't change direction. Fg is always down. Gravity always brings you down. So in this case, Fg does positive work, which is kind of neat. The only other one is about no work. So if I lift something, if I apply a force this way, but then I move the object perpendicular to the way that my force vector was drawn, so this is perpendicular at a right angle to, cosine of 90 degrees is 0, which means that technically this force can't do the work to move this object, whatever the object is. So here's the object now, but now we're moving it this direction. This is no longer doing the work. It does work to lift, right? So this force does work to lift it to this point, but if I then start to move it in a 90-degree angle from where it was originally, I now have cosine 90, 0. So remember that when you're doing this equation, FD cosine theta, theta can either be 0, 90, or 180, and that's it. This is negative, this is nothing, and this is positive.